Hello, so today we're going to be talking about quantum theory, very basic quantum mechanics that I'll expect you to know and to really apply throughout my class and the course year. If you want to go further into quantum mechanics, it's definitely something to look forward to in the rest of your academic career going into college. If you want to go deeper into physics or chemistry or really any science. But we're just going to kind of take a basic look at what it is today. So a little bit of background. Quantum theory was first proposed by Erwin Schrödinger in 1926. Schrödinger developed a mathematical relationship in which an observer could determine the position of an electron within an atom. So this goes back to Schrödinger's cat that we talked about in the previous episode. But he was actually able to define a mathematical proportion or relationship between the energy of an electron and the position of it at the same time. And the way this is demonstrated, it's demonstrated through this equation. Now, I know these symbols don't really make a lot of sense, so we'll just break it down a little bit. It's where E equals the energy of an electron, so that could be equivalent to momentum if needed. And there's a couple other things that this is actually the shortened version of the equation. The actual equation stretches out probably past this entire screen, but the more condensed version is this. This phi t is the wave function of the electron dependent on time. So again, going back in the previous video, electrons can act as both a particle and a wave. Well, when an electron is observed, it can act as a wave, which means the crest can determine its probability of location at a particular time. So electron could be in one place at one time, the electron could be in three places at one time. So this wave function helps determine the position of the electron. And then this h with the little arrow on top of it is called a Hamiltonian operator. It's a mathematical function that we use to help create a symmetry in this problem. So again, I don't expect you to know that, but just be aware that this is called Schrödinger's equation. So, and it's also referred to, or actually sets up what's called the particle in a box model, which is, again, pretty much Schrödinger's cat. So particle in a box, again, a foundation for the Schrödinger's cat analogy. You imagine that an electron is placed within a box with no way to escape. So we have a box here, there's an electron in there, no way to escape. But what we do is that at time zero, where the particle starts to move, this electron has a particular wave function. And what we can say is, it's a possibility if the probability is, let's say, this is zero, the probability of location is zero, then the electron's probably not even in the box at all, which could refer to electron tunneling and everything like that. But at one point in time, the electron, again, may not be detected in the box at all. This is due to quantum tunneling, electron tunneling, everything like that. So in this picture right here, it's saying that since there's no crest within that wave, it's just a straight line, there's no probability that the electron's in the box. Even though the box has been sealed up and we know that we put the electron in it, the electron was able to pass through the box somehow through crossing the gaps in between atoms and everything like that. Let's take it, if we take a look at it another time, right after we look at it the first time, we look at it again, we could determine if the electron's actually in the box. In this crest, that top portion of the crest is the probability that that electron is in that particular position at that time. So in this case, it just shows that with this wave function, the electron's only in one space that we can identify. But there is times that it can appear in two places. So again, we look at it again, excuse me, time 2, then it could have two crests in a wave function, which means that the electron is appearing in two places at once at one time. So I know it's a little hard to wrap your minds around, but since particles move so fast and they have this particle wave function duality, they have the ability to, at least on sensors and mathematically, be located in multiple places at one time. So this brings us to the quantum mechanical model, which we'll dive a lot into what that is in the next couple of videos. But it's the modern description of how electrons act within atoms. In this model, it states the motion of electrons cannot be defined on a particular path around the nucleus. So instead of those orbits that were in the Bohr model, the quantum mechanical model says there's just this cloud around the atom, and that those electrons can pop up in any place at any time, both in one place or in multiple. So they're just kind of scattering around pretty much at the speed of light, floating around the atom. And so we can either take a snapshot and see exactly where it is, or we can take a device and measure the energy of that electron at one time. So again, the position of electrons can only be described in terms of probability. So when we look at a cloud of electrons, we can only say it's probably going to be in this area. And that's what defines orbitals, which we'll talk about later on in other videos as well. Electrons occupy different orbitals or energy levels depending on the amount of energy that they have at a particular moment of time. So as light may hit an atom, it excites the electron, it puts it into a different orbital or a different position, and that electron gives that energy off and then jumps back into another orbital. So there's a lot of things that go around with electrons, which makes them really finicky and hard to deal with experimentation-wise. So we take kind of like a mercury atom here. You know, in the Bohr model, it said that all of its electrons are in this particular place. Now, it is true that only a certain amount of electrons can be in one orbit or orbital at a time. So like the first orbit right here, there's only 2. And that's due to the energy or the probability of how close you can put electrons together near the nucleus. As you get further and further out, you can pour more and more electrons into a single orbit or orbital at the same time. So, you know, it is quite possible that an orbit may be completely full at one point, and it can be completely empty at one point, or partially empty or partially full, whatever you want to say. It just depends on the time that you look at the atom or and electrons and the energy of the electrons at that time. So the biggest thing about the Bohr model, though, and in regards to the quantum mechanical model, is that the higher the energy of the electrons, the further the electrons are away from the nucleus. So the way I kind of look at it is like if you say, you know, the mercury atom is like planet Earth and electrons are satellites, okay? It takes more energy to put a satellite into further orbit away from the Earth than it would closer to Earth, because that rocket that shoots a satellite, which we can just say is the energy to take the electron up, has to be greater from the first orbit to the last orbit. So this electron up here has higher energy than the electron down here. So this is kind of, again, this is like an advanced version of the quantum mechanical model, but I just want to kind of show you what chemists and physicists do with this information. So this is kind of a basic quantum mechanical model of the bonding between a hydrogen atom and a fluorine atom, and how those electrons are separated into different energies and stuff like that. So again, the model to the right demonstrates an accurate version of the quantum mechanical model that you could find in literature, textbooks, stuff like that. This model utilized the shape of atomic orbitals to define the energy level and position of the electrons within atoms. So a couple of the pictures right here, these are the shapes of the orbitals that these electrons are bonding to, which means that, you know, the probability of this shaded portion means that there's a higher probability of electrons showing up in this compared to this. And then the same thing here, we have a tiny little orbital kind of bonded to a larger orbital here. So these shapes of orbitals do determine how electrons are arranged and what energy levels they can be at and how they can interact with other atoms and other electrons of other atoms and so on and so forth. To fully create a diagram like this, one must understand how to correctly write electron configurations, which we will dive very deep into in the next couple of videos because it's very, very important in regards to determining reactivity of atoms, how things are arranged within the nucleus and the atom and the electron cloud itself, and what exactly happens when you put energy into an atom, how those electrons actually shift and everything like that. So that's all there is for this video. Again, it's very short because I don't want to dive too much into quantum mechanics, and we actually need to for this class. This is kind of just a brief overview of how quantum theory was really developed and what it's really all about. So if you want to dive further into that, feel free to come talk to me. I can show you a couple of textbooks and references. Otherwise, I mean, when you go on further into your academic career, if you can take a class on quantum mechanics, I highly recommend it because it's the foundation of all modern science. Thanks for joining me on this video, and I hope to see you in the next one, and see you in class. Bye.